Welcome to this short session where I want to give you a motivation in which context we might refer to what we're going to learn here in calculus. When I say calculus, I mean in particular infinitesimal calculation, so working with derivatives, calculating extrema as in minima and maxima. Here we can start with typical optimization problems, or if you run a production line, want to optimize production, usually this means minimizing costs. So in our example, we can say, well, we produce 3 variants. The number of the variants are X, Y, and Z of a specific good. And the total costs accrued by the production per day can be determined by a cost function. Most like the cost function, depending on X, Y, and Z, so the number of variant X, the number of variant Y, and the number of variant Z produced. We have one part which increases the costs, one part which decreases the costs, and our question could be determine the cost minimizing output quantities. So which combination of X, Y, and Z should I select if I want to get the minimum costs? Well, this is one way to go about this problem, but usually I'm facing some kind of restrictions as well. One restriction, basically here, same type of problem, could be that in addition to the costs, I might have something like here, the company can produce 200 variants per day. And it also aims at realizing this output every day. So they really try to go for 200 goods each day. So in other words, the sum of all produced goods should be 200. Meaning, if we want to solve the same problem, we have an additional constraint, as in the sum is equal to 200. We have an equality constraint. Whenever we have an optimization problem, which also supports constraints, we're going to use the so-called approach of Lagrange multipliers. So that's the second part we're going to talk about. Unrestricted, unrestrained optimization problems, restrained optimization problems with equality constraints. That's one part. But you might also, in an assessment center, be faced with tasks like those parts here. So you have a rope, 200 meters of length, and you want to delimit a rectangular area as large as possible. So which sizes do the two sides of the rectangle need to have? Here, we're actually trying to maximize the size of the area. Well, the size of a rectangle is basically side 1 times side 2. So mathematically speaking, we're trying to find the maximum of a function f of x and y, x times y. But we still have an additional constraint. The 4 sides of the rectangle need to be exactly 200 meters long. So since it's a rectangle, 2 sides are the same. The other 2 sides are of the same size. I cannot assume that all 4 sides are the same. Then I would have a square and not a rectangle. So here, one set of sides, other set of sides. And if I subtract 200 meters, I should get 0. Or I could bring the 200 to the right side. Then I have like the sum of all 4 sides should be exactly equal to 200 meters. So again, I have a typical application for the Lagrange multiplier approach. Maximization of a function under a certain constraint. I can then expand this, for example, to which goods should I buy? Assuming I want to maximize the utility that those goods bring me, but I only have a certain budget available. That would be a different example where I can use the same method. So you can see there are actually a lot of problems which we can solve with this context. As soon as you want to get like the best or most efficient result in one context or another, it usually leads to an application of calculus.